Ladies and gentlemen, good evening. I decided to do another video which will consist of solving the problems given at the midterm exam, which happened some time ago, but I decided to do it now, better late than never. And also some of the problems we will solve some of the problems with material from chapter number 6, such as vector spaces or eigenvalues and eigenvectors. As you know, there were 6 problems. Let me show you the exam. This was the exam, right? As you can see it. So like I said, it consisted of 6 problems, total of 30 points. And the first problem was to solve the following system of linear equations. As you can see, it's a 3x3 system of linear equations. We'll see a bunch of methods here on how to solve this problem. The second problem was to find the determinant of, again, a 3x3 matrix. It's a very famous matrix with those ones and then ABC and the squares of ABC. This is what we call the van der Waals determinant. You can generalize this for 4x4 and even for n×n matrices. The third problem was to find the inverse of a matrix. And then I told you at the beginning of the video that I postponed to show you the solutions for this midterm exam long time ago because I wanted to use, for example, the characteristic polynomial, which was learned in the eigenvalues and eigenvectors chapter. In other words, this problem concerned finding the inverse of this matrix, again, a 3x3 matrix. And we'll see a bunch of methods here to finding the inverse of this. The fourth problem was to find the LU factorization of this 2x2 matrix. In other words, we want to write this matrix A as the product of a lower triangular matrix and an upper triangular matrix. And finally, the fifth problem, which was a proof-based problem, involves some relationship between the adjugate of the matrix and the matrix itself. Of course, we will assume that the matrix is not singular. Okay, so these were the problems. Let's get started. Let's start with problem number 1. In problem number 1, we have to solve the system. Let's write it. Solve the system, the linear system, S, which was 2x1 minus 5x2 plus 4x3 equals -3. x1 minus 2x2 plus x3 equals 5. And the last equation was x1 minus 4x2 plus 5x3 equals 10. So as you can see, it's a 3x3 system of linear equations, 3 equations, 3 variables. We'd like to solve this. And we will use 2 methods. And in fact, we'll give even a way of thinking at the end of the 2 solutions that we will present, how to spot if a system of linear equation has a solution or not. In fact, this is one of the, I don't want to say tricky, but it's one of the problems that, one of those systems that does not have any solution. In fact, we'll prove this. Let's look at the first solution. And the first solution uses basically just elimination. We would like to eliminate one of the variables. Well, in this case, if you look, we would like to eliminate maybe x1. Maybe there will be some ways of eliminating x1. Well, if you look at let's denote this equation 1. We'll denote this equation 2. And this will be equation 3. Right? Okay? Okay, we have this. And now we want to eliminate one of the variables, and we have our eyes on the first one, on x1. And let's see what we can do. In fact, we can do a bunch of stuff here. For example, we can multiply. So let's multiply equation 2 by -1. And let's see what we get. So we get an equivalent system. Let's call this S, right? It's the same thing. It's an equivalent system, which will be 2x1 minus 5x2 plus 4x3 equals -3, right? The second equation, we said we're going to multiply by -1, so we'll have negative x1 plus 2x2 minus x3 equals -5. And let's call this, okay, let's write the last one, x1 minus, okay, so here's a minus 4x2 plus 5x3 equals 10. Again, let's denote this guy. So the first two equations will stay the same. Let's denote this equation 2 prime, let's say, right? It's basically equation 2, but it's just the sign is changed. But let's denote it by 2 prime. Okay, now we can do some stuff. If you look at it, if we look at these two equations, let's say this again will be equation 3, and this again will be equation 1. All right. If you look at these two equations here, equation 2 and equation 3, as you can see, if I add them up, one of the variables, well, it's quite clear which one, x1 will just vanish. So let's do this, adding equation 2 prime and equation 3, we have the following. Let's see, what do we have? We have that negative 2x2 plus 4x3 equals 5, right? So this is the, let's denote this by star. This is what we get. As you can see, I have a relationship between this. And now let's do something else as well. Let me look again. And now what I'm going to do is the following. I'm going to multiply equation 3 by -1 again. And you will see why I'm going to do this. And we have the following. Again, it will be the same system S. Wait. So it will be 2x1 minus 5x2 plus 4x3 will be -3. Negative x1 plus 2x2 minus x3 equals -5. And the last equation will be negative x1 plus 4x3 minus 5 x3 equals -10. Again, let's denote this. This will stay again equation 1. This will be equation 2 prime, let's keep it like this, and this will be equation 3 prime. Okay. So let's look at this. Oh, wait. Sorry about that. So let's look at this equation, at this system now, and let's see what are we going to obtain. Okay, let's see. Now I can do the following. I can add all 3 equations. Once we do this, adding equation 1, equation 2 prime, and equation 3 prime, we have the following. Well, as you can see, x1 will vanish again, and we'll have what? We'll have x2, right? Minus 2x3, right? It will be negative 18. Let's call this double star. And now let's look at these 2 equations. This is very important. Let's rewrite them a bit. For example, if I multiply by negative 1, or maybe by negative 2, this guy here the equality, the above equality, right? The double star equality, we have the following. We'll have negative 2x2 plus 4x3 equals 36. And now let's see, let's look at this again. But also if we look around, if we look above, negative 2x2 plus 4x3 is 5. But equals 5, which is star. Well, which will imply that um, 5 equals 36. Well, so as far as I'm concerned, this will never happen when these 2 are real numbers, so we get a contradiction. Well, we assume that there exists x1, x2, x3 such that the system has a solution. We're looking for one, and we've seen that doing these kind of operations, eliminating one of the variables, which was in this case x1, we have seen that, well, bad luck. Nothing good happens. Therefore, there are no solutions. S right, so the system S does not have any solutions. All right, that's one way to prove this, by just using the traditional way of, well, just elimination. Basically, you don't have to do anything, just to look carefully at the system. Okay, but now let's see another method. And this method that we're gonna do is the classical methods. We will try to write the augmented matrix. So first, let's write the augmented matrix. of the system S. Which is given by the following. This is A. As you can see, I will write a coefficient matrix, and this will be bolded by the coefficients of the system. This matrix will look like this: 2, -5, 4, and this will be bolded by, let's write the matrix first: 1, -2, 1, 1, -4, and 5, and now this will be -3, 5, and 10. And what we're trying to do here is just to perform elementary operations to this matrix. As you can see, this matrix is a 3 by 4 matrix. It's not quite a square matrix, right? Since we bold it, so it's a 3 by 4. And what we want to do, like I said, we want to perform elementary row operations in such a way that we will end up with a matrix, an equivalent matrix in row echelon form, or maybe even better, in row reduced echelon form. And that's what we're going to do. And keep in mind what we're trying to do. First, if we look at this guy here as the dominant, we must transform this into a 1, and then everything below this should be a 0. So we will perform these elementary operations in such way. Okay, let's do it. As I already said, I have a 2 there, so I need to make it a 1, so it's quite clear what to do. I will take, let's say, okay, let me do it like this so it's clear. This is R1 here. Keep in mind that this is row 1, this is row 2, and this is row 3. Let's keep that in mind. Like I said, we will perform elementary row operations. So 1/2 R1 will become the new R1. Once we do this operation, we'll obtain the following matrix. This will be the following matrix. As I'm just doing these operations on the first row, the second and the third row will remain unchanged. So we will get what? 1, -5/2, 2, and -3/2. Okay, and then the second, second and the third, I'm just gonna copy them. Okay, and now let's see, what should we do now? Let's look. Maybe I should do the following. Maybe I should transform, well, yeah, why not? Let's do R1. Let's multiply R3 by -1, sorry, not 3. And this will become the new R3. Okay, and now we will have the following. Let's write it. Oh, maybe I should have written it here. Okay, on R3. So I said R1 plus -1 R3 will become my new R3. Okay, now we'll obtain the following matrix, right? The first two will remain unchanged. One, -2, 1, and 5. And now the last one, we said we're gonna, okay, so we'll have 0, -2, 4, and 5, right? Okay, so I have a 0 downstairs on the third row, but it bothers me that I have a 1 here. This guy here is a 1. So it kind of bothers me. I want to make it into a 0. So let's do that. And now what we're going to do, we're going to perform elementary operations on row 2. All right, let's see. Maybe I should multiply -1, the first row, by -1, then add it to the second row, and this will become my new second row. So -1 times R1 plus R2 will be R2. Okay, great. So we'll get the following matrix. 1, -5 over 2, 2, -3 over 2. And now we will have the following: 0, 1/2, -1, and here we will have 13 over 2, right? And the last one will be 0, -2, 4, and 5. Let me see. Yes, okay. Now what we're going to do, I have my zeros here, as you can see, below this 1, as you can see, this leading 1, I have zeros, and I have some fractions there. And if you look at row 2, maybe I should do something to it. I can get rid of some of the 2's there. Right? Let's multiply by 2. So 2 times R2 will be my new R2. Okay, great, let's do it. And we'll get the following matrix. 1, -5 over 2, 2. And this will be 0, 1, -2, and 13. And the last one is 0, -4, 4, and 5. Okay. Now it started to look more like a a matrix in row echelon form. So let's do some other operations and let's see what can we do. Maybe I should do something about the, row 1, and I think we can do something about it. We can transform this -5 over 2. Maybe we can make it transform it into a 0. Okay. In fact, let's multiply the second row by 5 over 2, and let's add it to the first one, and we'll get the following. So R1 plus 5 over 2. R2 will become my new R1. Okay, and let's see. So we'll get the following matrix. So we'll get 1, 0, -3, right? So the this will be 31 here, and then you'll get 0, 1, -2, 13, and the last one will be 0, -2, 4, and 5. Well, I hope I didn't do any mistakes in the computations. Well, and now guess what? What are we going to do will be the following, the last, because I want to look at the last one. As you can see, I'm almost there. Let's perform elementary row operations on the last one. So we'll have the following. We'll multiply, let's say, the second row by 2, and we'll add it to the third row. 2R2 plus R3 will become my new R3. And we'll get the following. 1, 0, negative 3, 31. 0, 1, negative 2, 13. And the last one, we said 2 times R2 plus R3, so we'll have 0, 0, 0, and 31. Well, guess what? Look at the third row. What happened? Well, if I want to go back to the system, right, by elementary transformations, look, I'll have 0 equals 31. This implies that 0 equals 31, which is false. So again, there is no solution. For our system S. Again, it's a system without any solutions. Well, I think these are the two ways of proving this. And now let me point out a remark before I jump into solving the second problem. How can you figure out that this system does not have any solution in the first place? Well, of course, you can follow the first or the second solution and then solutions, and you will see that the system does not have. You will get a contradiction. But also, before you even start, maybe there is something that could lead you to this conclusion. Well, let me remind you that the system S can be expressed in the matrix equation form. Remember that this matrix equation form was AX equals B, where A will be, of course, the coefficient matrix, which will be 2, negative 5, 4. It will be a 3 by 3 matrix, 1, negative 2, 1, and the last one will be 1, negative 4, and 5. Our vector X will be X1, X2, X3, it's a column vector, and of course, the coefficient vector will be B, which is B1, B2, and B3, right? And keep in mind that this B here, maybe I should have said this. Okay, let me write it explicitly. It was negative 3, 5, and 10. So this is my B. Okay, maybe I should write it like this, where this is A, this is X, and this is B. So that's the equation. What do we know about this equation? Usually this matrix equation, we have said in one of the lectures, I think it was lecture number, I don't know the number, but I think it was chapter 3. This matrix equation has a unique solution X is A inverse times B, right? We know this. We have proven this, and it's very easy to see. You just multiply by the inverse of A to the left, and then you'll get X equals A inverse times B. But guess what? Well, usually this is what happens, but well, we're making a big assumption right here. How do I know that the matrix A is invertible? Maybe it's not. And I'll leave it to you to answer this question. If A is invertible, we will see that maybe not. And maybe that will tell you that, okay, maybe there is no solution to this system. So that's the way to think of this problem. Okay, I think I'm going to end up the solution here for problem 1. I think there are plenty of ways of doing this. I just showed you 2 ways that I found easy. And now let's see the second problem. Problem number 2. I have this matrix. Let's write this matrix, a 3 by 3 matrix. Like I said, is a very special matrix. And we want to compute the determinant of A. Well, this is the determinant. Sometimes we denote it by this, but anyway, it's just a notation. It doesn't really matter that much. Like I said, there are plenty of ways to do this. Let's see. Well, it's a 3 by 3. You can do it in 3 ways. In fact, maybe at least 3 ways. Yeah, we'll do it. You give 3 solutions to this. Let's see the first solution. Well, if you look at it, I have a bunch of 1s here on the first row. Maybe I should expand on the first row. Expanding on the first row will give us the following. Let's see. So the determinant of A will be 1. Okay, let's rewrite it in this way. Negative 1 to the power 1 plus 1 times 1 times the minor of the element, well, the first row, of the entry on the first row and first column, which will be this determinant, b c b squared c squared, plus negative 1 to the power 1 plus 2 times 1 again. And again, we'll have the minor, so it will be ac, the determinant of ac and a squared c squared, plus the last one will be 1 times negative 1 to the power 1 plus 3 times ab a squared b squared. Okay, that's easy to do from here. You'll see I have just a bunch of plus and minuses here. So this would be equal to bc b squared c squared minus a c a squared c squared plus the determinant of a b a squared b squared. Now it's easy to compute each determinant. The first one will give us bc squared minus b squared c minus ac squared minus a squared c plus AB squared minus A squared B. Well, you can leave it like this if you want. We can factor if you want, but you'll see that we'll obtain different expressions, or maybe the same expressions, which are by just the elementary algebra, just in will be the same thing. Okay, that's the first thing. We use in this first solution, we expand on the first row, right? Since I have a bunch of ones. But now, let me give you another solution, which is a little bit more, I wouldn't say tricky, but it involves the properties of the determinants. And we said one thing in class. We said that we can perform elementary row operations to find, to solve systems of linear equations, to find the inverse of a matrix, and so on, right? But we said one extra thing involving the determinants of a matrix. We said that we can perform the same elementary operations not just on rows, but also on columns, if our purpose is to find the determinant of a matrix. Well, let's do this. This is the right time to do this. The best example, we use properties of the determinants. Indeed, we have. Okay, so let's do this. And now what I'm going to do is the following. Look at the matrix. In fact, let me write it. The determinant, let me write it again. It's 1, 1, 1, A, B, C, A squared, B squared, C squared. Okay. And again, I'm looking at this row here. But what I'm going to do is the following. I'm going to perform, I will also look at the columns, right? Say this is column 1, this is column 2, and this is column 3. We can perform the same elementary operations. And now we're going to do the following. This will be nothing else than just, I'm going to keep the same column here. 1A squared. So this will be column 1. And now in column 2, what I'm going to do is I'm going to take column 2 and subtract column 1. So column 1 minus column 2 minus column 1 will be 1 minus 1 will be 0, b minus a, b squared minus a squared. And now on column 3, I will take column 3 and subtract column 1, which will give us again 0, c minus b. Wait, what am I doing here? Sorry. C minus a. And c squared minus b squared. Minus a squared, I'm sorry. Right? Okay. And now what I'm going to do, I'm just going to expand. If you look, I have a bunch of zeros here. I'm just going to expand on the first row. So let's do this. Once we do this, expanding. Oh, it's kind of similar to the first solution, but this uses a little bit of properties of the determinants. Imagine if you had like a 4x4 matrix. When you expanded all those 3x3 minus, that would have been really painful to do so. Now expanding on the first row, we have following. The determinant of A is, as you can see, I can only expand on the, so have negative 1 times 1 plus 1 times 1, which will be B minus A, C minus A, B squared minus A squared, right? Now, once we write this, this will be nothing else than just B minus A times okay? And now if we multiply this, if we go further, this will be and this will give us we can factor B minus A times C minus A, B minus A which gives us nothing else than just B minus A times C minus A times C minus B, right? Well, if you multiply all this, and I'm going to leave it to you as an exercise, we're going to get this. Guess what? This is nothing else than just equal to this. They're the same thing. I will now leave it to you as an exercise. All right, and now the third solution. We want to use the so-called Cezar's rule. Again, this rule usually this rule works only on also on the columns if you want, but we're going to copy the first two rows. So let's do this. Let's write the determinant. Now I'm going to do the following. I'm just going to copy the first two rows. And now what I'm going to do is the following. I'm going to multiply these elements plus this element, multiplication of this, plus the multiplication of this, minus, let me write with a different color. The multiplication of this, minus multiplication of this, minus this. And we'll get the following. Right, let's write all this mess here. We'll see. We'll have BC squared plus AB squared plus A squared C minus A squared B plus B squared C plus AC squared. Right? And as you can see, we can group this together. Let's do this. We'll have BC squared minus BC, B squared C plus AB squared minus A squared B plus A squared C minus AC squared. Great. Again, if you look closely, this will be nothing else than just what we previously got here. It's exactly the same as in solution 1. But I'll leave it to you as an exercise to convince yourself that this can be expressed as the product of A minus B, B minus C, and C minus A, just like we got in the second solution. Okay, I think this is this is problem number 2. Now let's move to problem number 3. Problem number 3 concerned finding the inverse of, again, a 3 by 3 matrix. This was matrix A, which had the entries 2, -1, 3, 0, 1, 1, -1, -2, and 0. Again, this is a 3 by 3. Okay, it says find the inverse of this matrix. Basically, we wonder who this guy is. But how do we know that the inverse actually exists? Well, there are some ways to show this, and we will see that in fact we'll give 3 solutions to this problem. And the third solution will use what we learned in the eigenvalues and eigenvectors chapter. Basically, we'll use the characteristic polynomial. We won't go that far in using the eigenvalues of A. But first, let's go and do it in the classical way. And the most classical ways, this is not the way I learned when I was in high school. I learned it using the adjugate of a matrix. You know, I had to compute all the cofactors and then to transpose a cofactor matrix after. Of course, at first you need to compute the determinant and show that the determinant is in fact non-zero, so that you can conclude that A is invertible. So that's the way I learned. We will see this approach. This will be the second solution. Well, now let's do it just like we learned. Solution 1. So what I'm going to do, again, I'm going to perform elementary operations on matrix A, which will be to which I will adjoin the identity matrix. Well, let us adjoin the identity matrix. Let's call this I3. So that you will know that it's a 3 by 3 to the matrix A. And guess what? This will be a 3 by 6 matrix. Let's write it. And I'm going to write it in the following way. I hope I have enough room. A3. And I'm going to A and the identity. And I'll perform elementary operations in such way that I will, instead of at the end, I have to the identity will be on the left, and then another matrix will be on the right. And guess what? That matrix that will appear on the right will be nothing else than just the inverse of A. Okay, let's write the matrix. Like I said, it will be a 3 by 6. Okay, let's copy 2, -1, 3, 0, 1, 1, -1, -2, 0. And now we'll just copy here the identity. Okay. You see, here on the right I have the identity, on the left I have the matrix. Now I have to perform elementary operations. First, let me say that this is not a square matrix, it's a 3 by 6 matrix. As you can see, it has 3 rows, 6 columns. And now I will perform elementary operations in such way so that I will obtain on the left, I will get the identity, and then on the right I'll get another matrix, which will be nothing else than just the inverse of A. Okay. Let's do it. Let's see, what can we do? Let's look at, okay, I see here a bunch of, on the first row, So keep in mind, I want to transform all this from A in as many zeros as possible. And I look at row 1 and row 2, I see a -1 and a 1. So maybe I should add yeah. Okay. So we'll have the following. Let's see what. So let's. In fact, I'll do the following. Let's add R1 plus R3, and this will be my new R1. Okay. Once we do this, we have the following matrix. 1. In fact, let me write it here. Okay, now have, this will be 1, -3, 3, 0, 1. Okay, and here I'll have 1, 0, 1. Here I'll have 0, 1, 1. Okay, great. And now what I'm going to do, I'm going to add R1 plus the first row and the third row, and this will be my new R3. Okay, let's do this. R1 plus R3 will be my new R3 this time. We'll get the following. So we'll get 0, -5, 3, 1, 0, 2. Okay. Okay. And now what I'm going to do, so keep in mind, I want to make, I always have this purpose in mind. I want to make the matrix on the left-hand side to make it look as much as I can as well, I have to make it look like the identity. Let's see. What else can we do here? What if we multiply? As you can see, I have a -5. Maybe I should get rid of it. What if we multiply the second row by 5 and we add it to the third row, and then this will be my new R3. Okay, let's do it. Uh, 5R2 plus R3 is my new R3. We'll have 1, -3, 3, 1, 0, 1, 0, 1, 1, 0, 1, 0. And the last one will be 0, 0, 8, 1, 5, 2. Wow, great. As you can see, I have these ones here. I have an 8 there. All right, no problem. Now, let's see something else. I also have a -3 here. If you look at it on the first row, maybe I should get rid of it. So what to do will be the following. Maybe I should multiply the second row by 3 and add it to the first row. Let's do this. So we said second row by, so R1 plus 3R2 will become my new R1. Okay, let's see this. Oh. So it will be 1, 0. So we said R1 plus, okay, 6. Okay, 1, 3, 1. Right? And then the second, so it will be 0, 1, 1, 0, 1, 0, 0, 0, 8, 1, 5, 2. Okay, and now guess what? Everything looks very nice, almost there. Let's look at the third row, and we have this 8 here. And I'm going to multiply by 1 over 8. 1 over 8 R3 will be my new R3, and we'll get the following matrix. We'll get 0, 0, 1. And here you have 1 over 8, 5 over 8, and 1 over 4. Okay, beautiful. But we're not done yet. There is one last thing we need to do. So I have a 6 there. Okay. Let's multiply . Okay. So I have this 6 here. Let's multiply the last row by -6 and add it to the first row. Okay, let's do this. Right, okay. So R1 plus -6 R3 will be my new R1, right? And we'll get the following matrix. We'll get 1, 0, 0. And here we'll have 1/4, -3/4, and -1/2. Wait, I think I forgot to do an operation. No, wait, not yet. I jumped one step ahead. No, okay. Now what I'm gonna do, so I have, okay. Now let me do, no, we have one more step. Now let's look at R2. Yeah, because I forgot here, there is a 1 here, so I'll have to get rid of it, right? We have to make it look as a 0. So I don't want to. So we have to do an operation with 2R2. And what we're going to do will be the following. Let's multiply R3 by -3. And add it to R2. And we'll get the following. Let's write it here. R2 plus -3 times R3 will be my new R2. Okay, we'll have the following. We'll have 106, 131, and then the second one will be 2, okay. It'll be 0, 1, 1 minus -2, right? And here I'll have -1/8, 3/8, -1/4. Okay, and on the last one, I have 0, 0, 1. And here we have -1/8. Wait, it's 1/8, sorry. 5/8 and 1/4. Right? Okay. Okay, yeah, okay. And now the last one, we'll have the following. We want to transform, we kind of want to get rid of this 6 here. So we'll have the following. I'll perform operations on R1. So let's multiply the last row by -6. So we'll have R1 plus -6 R3 will be my new R1. Okay, and finally we'll get what we want. And finally we'll have here 1, 0, 0, 0, 1, 0, 0, 0, 1. Perfect. And here we will have the following. We'll have 1/4, -3/4, -1/2, -1/8, 3/8, -1/4, here I'll have 1/8, 5/8, and 1/4. Guess what? Now, this is nothing else than just the identity, if you look at it. And here, this is followed by this matrix that is nothing else than just the inverse. So as you can see, we started doing elementary operations. We started with this here, well, right? And we ended up with this. Well, clearly, this guy here will identify as the inverse of a matrix. In other words, we have that A inverse is nothing else than just this matrix. 1/4, -3/4, -1/2, -1/8, 3/8, negative 1/4, and the last will be 1/8, 5/8, and 1/4. That's the inverse of a matrix. Okay, as you can see, we did elementary operations here. Well, it was a bit of a work, but it wasn't that hard. We just had to be careful about it. And now, let's look for solution 2. We use the following formula. Well, that's how I learned it in high school. I'm gonna write it. A inverse is nothing else, provided that that inverse exists, than 1 over the determinant of A times the adjugate of A. That's the formula. And this guy here is nothing else than the adjugate of the matrix A. Well, you will see what the adjugate is because we will compute it. It's nothing else than just the cofactor matrix transpose. Okay, let's, oh, there's going to be a lot of computations here. First off, we need to compute the determinant. Well, and we can do this as you have seen in the previous problem in many ways. Well, let's see. For example, we can use Sato's rule. Let's write again, 2, negative 1, 3, 0, 1, 1, negative 1, negative 2, 0. Anyway, I'll leave it to you as an exercise. At this point, based on the previous solution, I already know what the value of this determinant is, in fact, 8. And I'll leave it to you to actually see that. Okay, now we want to compute the adjugate of a matrix. Keep in mind that a cofactor matrix is given by, let's call this C. It has this complements, the algebraic complements C11, C12, C13, C21, C22, C23, C31, C32, C33. Okay, so that was the cofactor matrix. But now guess what? The adjugate is nothing other than just the transpose of this cofactor matrix. Let's write it. The adj of A, the adjugate of A will be the cofactor transpose, which will be nothing else than just C11, C12, C13. We're going to write them on the column. C21, C22, C23, and C31, C32, C33. Okay, beautiful. Now we have to compute the algebraic complements. Oh my goodness. Let's do it. C11, keep in mind that this will be negative 1 to the power 1 plus 1 times the minor. Let's look at the matrix. So it will be uh, 1, 1, negative 2, 0. Which will give us, well, according to my computation, this will be 2. Then C12 will be negative 1 to the power 1 plus 2 times C12, 0, 1, negative 1 is 0. This will be negative 1. C13 will be this guy. times 0, let's see, 2, 1, 3, 0, 1, negative 1, negative 2, which will give us 1. And now let's move to the second one. C2, 1 will be which will be negative 6. C2, 2 will be which will give us 3, right? Okay. All right, and there's 3 more to compute, and then we're done. So okay, more. C2, 3 will be 4 of them. Which will give us 5. All right, and finally the last 3. Which will give us C3, 2, wait, C3, 2, okay, which will give us negative 2, and finally C3, 3 is negative 1 to the power of 3 plus 3 times 2, negative 1, 0, 1, which is 2. Now finally, the inverse is given by this guy here, which is 1 over, let's write it again, 1 over the determinant of A times the adjugate of A, which is nothing else than 1 over 8 times the matrix 2, negative 6, 4, negative 4, sorry, negative 1, 3, negative 2, 1, 5, 2. And again, if you plug in 1 over 8 inside the matrix, it will give you nothing else than just what it's 1/4 minus 3/4 minus 1/2 minus 1 over 8, 3 over 8, negative 1 over 4, 1 over 8, 5 over 8, and 1 over 4. Okay, great. That's the inverse of A. Well, it's kind of long. It's basically it uses a formula and that's it, and you just need to compute the adjugate of A. Well, it kind of requires a little bit of knowledge. It's not definitely, it doesn't look like the first solution where you just play around with elementary transformations and there you go. Well, this is how I learned it in high school in Romania. But also there is frankly, once you see the third solution, which I like the most, to be honest with you, you will see that this second solution in computing the adjugate and everything like that, it's very not practical at all, as far as I'm concerned. Anyway, now let's see the third solution. And this one is a beauty. Using the characteristic polynomial of a matrix. Okay. And And you will see that here there is no need for us to compute the eigenvalues of a matrix. We just need to compute the characteristic polynomial. And let me remind you that the characteristic polynomial of a matrix, PA of lambda, is nothing else than just the determinant of lambda times the identity minus A. And now we can actually compute this. First, let's, so this will be the determinant, let's write it, of the following thing. The identity lambda times the identity will be lambda 0, 0, 0, lambda 0, 0, 0, lambda minus the matrix A, which will be 2, negative 1, 3, 0, 1, 1, and negative 1, negative 2, and 0. Okay. Now we have to compute the determinant of this. This will be nothing else than just the determinant of, or maybe I should write it in this way. Lambda minus 2, 1, negative 3, 0, lambda minus 1, negative 1, 1, 2, lambda. So I have to compute the determinant of this. And I'll leave it to you as an exercise because I want to skip some computations. I have already done them. So this will be for you to convince. It's like an exercise. This will be nothing else than just, according to my computations, lambda cubed minus 3 lambda squared plus 7 lambda minus 8. Okay, so this is the characteristic polynomial. And now we know one thing here. So let's write it again. It's a degree 3 polynomial, as you might expect. Okay, this is the characteristic polynomial. And now, I'm trying to do something. So basically, I'm trying to find the inverse of a matrix using the characteristic polynomial. Let's see, how should we do this? Well, there is one thing that we have learned in the eigenvalues and eigenvectors chapter that sounds a little bit like this. The Cayley-Hamilton equality says the following, and we have seen it explicitly written for 2 by 2 matrices. It says that PA of A is nothing else than just the 0 matrix. In other words, if we plug in, for lambda, we plug in the matrix A, we'll have the following. A cubed minus 3 A squared plus 7A minus 8 times the identity is, which is equivalent to this is equivalent with the following. And now let's do some operations. Let's take, so A cubed minus 3A squared plus 7A equals A times the identity. And now what we're going to do, since we know that the inverse actually exists, we have seen that the determinant is non-negative, let's multiply to the left by A inverse, and we're going to get the following. A squared minus 3A plus 7 times the identity, right, equals 8 times A inverse. Or we can actually divide by 8, or A inverse will be nothing else than 1 over 8 times A squared minus 3A plus 7 times the identity. That's the inverse of A. Well, now if you want, you can compute, you can do the computations and you will see that, in fact, let's do them. So now we want to see who this guy is. A squared minus 3A plus 7 times the identity. This is nothing else. If we want to compute this, well, the A squared, let me see, I have some computations here for A squared. It's 1, negative 9, 5, negative 1, negative 1, 1, negative 2, negative 1, negative 5. Okay, minus 3 times the times A, which is 2, negative 1, 3, 0, 1, 1, and negative 1, negative 2, 0. Okay, plus 7 times the identity. Okay, and all this mess here, all this computation here, if you want to do it, will give us the following. 2, negative 6, negative 4, negative 1, 3, and negative 2, 1, 5, 2. Okay, great. Finally, now the only thing you need to do is just divide by 1 over 8. A inverse is nothing else than just 1 over 8 times 2, negative 6, negative 4. And finally, this will give us nothing else than just what you have, 1/4, negative 3/4, negative 1/2, negative 1/8, 3/8, negative 1/4, and the last one is 1/8, 5/8, and 1/4. That's the matrix. That's the inverse matrix of A. And that's it. That's problem number 3. Well, as you have seen, 3 solutions, 3 different solutions for this. Now let's move to problem number 4 quickly. Problem number 4, well, it was the following. We need to find the LU factorization of this 2 by 2 matrix, which is 3, 1, and 4, 2. What is an LU factorization? Well, let me remind you. So A is can be written as a lower triangular matrix, right, times an upper triangular matrix. Well, the question is if we can write this, and if so, what is the LU factorization? So we need to find who these 2 guys are. Let's call this, well, this L and this U. We need to find who this L and U, these 2 matrices are. Well, as you can see, if you look at the upper corner determinants here, these both of them are non-zero. Definitely, we will have an LU factorization. I think we've done this in one of the review sessions a long time ago. And we've seen under what conditions we do have an LU factorization for a square matrix. And now let's see. Well, we'll give two solutions for this. Well, you have seen that A can be expressed as LU. This will be equivalent with this is 3, 1, or 2. And this is nothing else than we always buy some elementary transformations for, we'll always end up with the lower triangular matrix. The lower triangular matrix will always end up with 1 on the main diagonal. That's the trick. You'll have a 0, and here you'll have an element, let's call this L21, right? Times, this will be, this is A, this is L, and this guy will be U, which is U11, U12, 0, and U22. Like I said, it's just a generic upper triangular matrix. And now guess what? We're just going to do basic algebra. We're going to multiply. We're going to do this multiplication here of L and U. This implies the following system of equations. Okay, let's see. All right, let's look at it. If we multiply L and U, just like I said, we have that U11 will be 3. Then U12 will be 1. Then L21 times U11 is 4, which will imply that L21 is 4 over 3. And then the last one, if we multiply L21 times U12 plus U22, right? It will be 2, which will imply that U22 is 2 minus 4 over 3, which is 2 over 3. Well, that's beautiful. Now we have everything we need. It follows that LA, matrix A, can be expressed as the product of a lower triangular and an upper triangular matrix, which will be 1, 0, 4 over 3, 1. This will be L, and U will be nothing else than just 3, 1, and 0, 2 over 3. Right? That's it. The main thing is to observe that this will always be the case here. That on the main diagonal of the lower triangular matrix will always have 1s. This will always happen. I think I've explained this in the lecture. And the solution to, well, this is more a traditional approach. We have done this in when we found the LU factorization of a 2 by 2 matrix. And now what we're going to do is the following. I'm going to take the matrix A. So take A, which is 3, 1, 4, 2, right? I'm going to take this matrix A, and I'm going to perform elementary operations on this one such that I will, okay, let me do it this way. And perform elementary row operations such that we end up with an upper triangular matrix. This is important. So we'll perform elementary operations in such way. Okay, let's do it. And I'm going to do the following. I'm going to write the following chart. So I have the matrix A, elementary operations. And here I will have the elementary matrix. And let me remind you that the elementary matrix is obtained from the identity by performing one single row operation. Okay? Let's do it. So let's say the matrix A. A is 3, 1, 4, 2. Okay, and keep in mind that I want to end up with an upper triangular matrix. It's quite clear what I need to do. And the elementary row output, giving the fact that I want to end up with an upper triangular matrix, just like we said here. The elementary row operation will be to multiply the first row. So this is, let's hear it, it's R1, this is R2. And the elementary operations that I want to do is the following. Let's multiply -4/3 times R1 and add it to R2, and this will become my new R2. Well, it's quite obvious that's what I need to do. And my elementary matrix, keep in mind that we start here with the identity. And I'm going to perform the same operation on the identity because we said that this is what an elementary matrix is. We obtain it from the identity by applying a single row operation. So we will apply this row operation and we'll end up with the following. Let's call this, we'll call it directly U because we'll obtain it in a upper triangular form. It will be 3 or 1. So the first row will stay the same, but the second will be 0 and 2/3. Okay, and here we'll have this elementary matrix, let's call it elementary 1, E1. We said we're going to perform the same thing, so we'll have 1, 0. Keep in mind that we always look at the identity, and will be -4/3 and 1. Wow, look at it. I have already the ones here on the main diagonal. Wow, that's beautiful. So in other words, this will be L. Well, not quite L. Well, almost. What we did is the following. And you know, by performing this element, you know that any matrix can be written as the product of elementary matrices, but starting from left to right. In other words, we'll have that E1 E1 times A will give you the matrix, the upper triangular matrix U. And now what I need to do, I just need to write A. Well, that's quite clear what to do. We multiply to the left by, you know, the elementary matrices, we know that they're invertible by A inverse. And now we have that A will be nothing else than just E1 inverse times U. Well, this U1 inverse, which I will identify as the lower triangular matrix, is nothing else than just the inverse of this matrix, and the way we're going to obtain this will be the following. We're just going to apply the reverse row operation to E1. We'll have the following. This will imply that E1 inverse is nothing else than just, so applying the inverse, so it's 4 over 3 R1 plus R2. So it will be 1, 0, 4 over 3, 1. And I will identify this as L. Well, as you can see, now it's very clear that A can be factored by as LU, where L is 1, 0, 4 over 3, 1, n times U, which is given by, we said 3, 1, 0, 2/3. As you can see, they're the same two matrices as in the previous solution. And again, on the lower triangular matrix, I have these ones here. So this is L, and this is U. That's it. The solution for this problem ends here. Okay, now we're moving to the last problem. Problem number 5. And keep in mind that we had to prove a bunch of things about so problem number 5 said the following. Let A be a singular matrix. I'll assume that these are an n by n singular matrix. Again, n by n matrix. I will not assume that it's a 2 by 2. And we have to prove a bunch of things. Well, we have to prove and let the adjugate of A. Okay. So we had to prove that we can express the determinant of a matrix in terms of the determinant of the adjugate of a matrix in terms of the determinant of a matrix, right? That was the first, and then we can express the adjugate of a matrix in terms again of the determinant of a matrix. In other words, the problem said the following, and this is more, it's a proof-based problem. Well, the determinant of the adjugate of A is nothing else than just the determinant of A, everything to the power n minus 1. And then the second part is to show that the adjugate of A is nothing else than just the determinant of A to the power n minus 2 times A. Well, when I look at your paper, some of you just gave me an example of a 2 by 2 matrix. Well, yeah, I'm sure it will verify these properties, but I didn't ask you to do that, to verify these properties for a bunch of matrices. What the problem asks is to prove these. So let's do it. Like I said, this is the hardest problem in the exam. Like I said, the last problem always, the last two problems always going to be like something to prove. And these type of problems will require a little bit of thinking. Okay, let's see. What do we know about the adjugate? Keep in mind, wait. What did I say here? It's a non-singular matrix? I don't think so. Not a singular matrix. It's kind of late, so. Okay, this is a non-singular n by n matrix. Well, we know that non-singular matrices, basically it's the same thing as, it's equivalent of A being invertible, and therefore the determinant is non-zero, right? And moreover, we can express, we have seen this in one of the lectures, we can express the product of A will commute with the adjugate of A. And let me rewrite this. A times the adjugate of A will always be equal with the adjugate of A times A. And this will be nothing else than just the determinant of A times the identity. So that's the relation we need to keep in mind. Well, now guess what? Since let's look at the first one. I'm trying to find some information about the determinant of the adjugate of A. Well, it's quite natural for me at this point to take to apply the determinant in one of these equalities. Applying the determinant. We have the following. Let's look. The determinant of A times the adjugate of A is nothing else than just, well, it doesn't matter. The determinant of A times the adjugate of A is the same as the determinant of adjugate of A times A. The determinant is multiplicative, so we don't care about this. We only care about to look at this one here, the determinant of A times the identity, and this will be, keep in mind by the properties of the determinants, this is a scalar here, and you know that the scalar will go outside the determinant, and but this will be the determinant of A to the power n times the determinant of the identity. But we know that the determinant of the identity is nothing else than just 1. So this will be the determinant of A, everything to the power n. Well, great. But we know, so at one hand, we know that the determinant of A times the adjugate of A is the determinant of A to the power n. But on the other hand, we know that the determinant is multiplicative. So we have that the determinant of A times the adjugate of A is the determinant of A times the determinant of the adjugate of A. Great. So we obtain that the determinant of A times the determinant of the adjugate of A is nothing else than just the determinant of A to the power n. And now we can, since we know that the determinant is non-zero, we can divide by the determinant of A, which is non-zero, and we'll get that the determinant of the adjugate of A is nothing else than just the determinant of A to the power n minus 1. And that's the first equality we had to prove. You see? Basically, it was just an application of this identity here. And properties of the determinants, nothing else. Okay, now we want to make use of this property in a little bit different way. Look at what I have to prove. In fact, I can do even more. I can express the adjugate of A in terms of the determinant of A and the matrix A. Well, that's great. What I'm going to do now, I'm just going to apply this identity, but instead of A, I will apply it for the adjugate of A. So by the same reasoning, we obtain the following identity. Okay, let's look at it. So we'll have that the adjugate of A times the adjugate of the adjugate of A. It's nothing else than just the adjugate of the adjugate of A times the adjugate of A, which will be equal to the determinant of the adjugate of A times the identity. Let's keep this in mind. Okay. But now, we know something about the determinant of the adjugate of A. So from here we have that, let's retain the following information. The adjugate of A times the adjugate of the adjugate of A is nothing else than just the determinant of the adjugate of A times the identity. Okay. But now if I look at the first part, this guy can be, we have proven, right, that this guy is nothing else than just the determinant of A to the power n minus 1, right? This is from part I. So this implies that the adjugate of A times the adjugate of the adjugate of A is the determinant of A to the power n minus 1, right? And now we need to do something, and because maybe I should multiply to the left by A, multiplying by A will give us the following: A times the adjugate of A times the adjugate of the adjugate of A, which is nothing else than just A times the determinant of A to the power n minus 1. Anyway, it doesn't matter, the determinant is just a scalar. But this guy here, now we're going back to our first identity. Let me go back, look here. A times the adjugate of A is the determinant of A times the identity. This guy here is nothing else than just the determinant of A times the identity, right? And this guy here is the determinant of A to the power of n minus 1 times A. Finally, we obtain what do we obtain? We obtain the following. The determinant of A times the identity times the adjugate will be this, just the adjugate of A, which will be the determinant of A to the power n minus 1 times A. And now I'm going to divide by the determinant of A, since it's different than 0. And this will give us that exactly what we wanted, that the adjugate of A is nothing else than just the determinant of A raised to the power n minus 2 times A. And that's exactly what we wanted to prove. Ooch. And that's it. Okay, this finalizes the solutions of the problems for this midterm exam. I'll stop here. Thank you very much.